An object smaller than a city could wipe out every credit card on Earth from a distance of 192,000 kilometers. It's not a black hole, not a supernova, but a slowly spinning dead star with a magnetic field 10 million times stronger than anything humans have ever built. That thing exists right inside our own galaxy, and the real question is, what happens if it's ever closer than that? Here's something that runs against everything you'd assume about the universe. The single most powerful magnetic object ever measured is not a black hole. It's not even close. Black holes are famous for their gravity, for swallowing light itself, but when it comes to raw magnetic force, something smaller and far less famous takes the crown. Scientists call it a magnetar, and if you've never heard the term before, you're not alone. Even among dedicated space enthusiasts, this is one of the least talked about objects in the entire cosmos. Part of the reason for that obscurity is sheer scarcity. Out of the thousands of neutron stars astronomers have catalogued across the Milky Way, only about 30 have ever been confirmed as magnetars. That makes them one of the rarest classes of object in the entire galaxy, rarer in relative terms than nearly anything else astronomers study on a regular basis. So what exactly are we talking about physically? A magnetar is not some sprawling giant sphere of gas. Its diameter is only around 20 kilometers, roughly the footprint of a small city, something you could drive across in a matter of minutes. And yet, packed into that impossibly small space is a mass roughly 1.4 times that of our Sun. Sit with that contrast for a second. An object you could walk across in an afternoon, carrying more mass than the star that lights our entire solar system. The concept itself is relatively young in scientific terms. It was astrophysicists Robert Duncan and Christopher Thompson who first proposed the idea in 1992, coining the term magnetar and laying out a theoretical mechanism for how such an object could form in the first place. What began as a theoretical proposal on paper has since become one of the most extreme confirmed objects in observational astronomy, proof that something this small can quietly hold more raw power than anything else we know how to measure. But knowing that something this compact carries this much force only raises the obvious next question. What, exactly, is producing that kind of strength in the first place? Let's start with a number that's almost impossible to hold in your head. A typical magnetar's magnetic field measures around 1015 Gauss, 1 quadrillion Gauss. Earth's own magnetic field, the one that keeps your compass pointing north, sits at roughly 0.5 Gauss. That comparison alone should tell you something is deeply wrong with how we normally think about magnetism. Unlike Earth's field, which stays remarkably stable year after year, a magnetar's field is anything but calm. Its crust can actually crack and shift under the stress of its own magnetic tension, triggering what scientists call a starquake, a violent rupture that releases enormous bursts of energy in the form of X-rays and gamma rays. Have you ever stood near an MRI machine and felt that quiet, invisible hum of power, strong enough to yank metal objects clean across a room? A magnetar's field is roughly 100 million times stronger than that same medical MRI magnet. Multiply the strongest machine your local hospital owns by 100 million, and you still haven't reached the field strength radiating from an object smaller than most city blocks. It's the kind of number that stops making intuitive sense the moment you try to visualize it, which is exactly why comparisons like this exist in the first place, to give your brain something, anything, to hold on to. And the effects go even further than raw magnetic pull. Astronomers have measured magnetic fields around magnetars strong enough to visibly curve the fabric of spacetime itself, a distortion effect previously associated almost exclusively with black holes or entire galaxies. When a magnetar's crust finally does crack under pressure, the energy conversion is astonishingly efficient. Nearly 100% of that magnetic energy gets converted almost instantly into a burst of X-rays. Picture a simple demonstration you could actually try at home. Sweep a strong neodymium magnet quickly past a coil of wire, and you'll generate enough current to light up a small LED bulb with no battery attached at all. That's basic electromagnetic induction. The same principle at work here, just scaled up by a factor almost too large to comprehend. Your own body, full of water and dissolved ions, conducts electricity too, which means a strong enough shifting magnetic field could, in theory, generate a current directly inside you. Of course, producing a current that's severe requires a field vastly stronger than anything humanity has ever engineered, which is precisely the threshold that only a magnetar can cross. Its magnetic field doesn't just pull on things from a distance. It reaches in and tears them apart at the atomic level. On December 27, 2004, something extraordinary happened, and almost nobody outside the scientific community noticed at the time. A colossal burst of energy from a magnetar named SGR 8620 swept across our planet, briefly disrupting Earth's ionosphere, the electrically charged layer of atmosphere that satellites and long-range radio signals depend on. What makes this genuinely hard to process is the distance involved. That magnetar sits roughly 50,000 light-years away, on the far side of our own galaxy, and its burst still managed to physically nudge conditions in our upper atmosphere. Have you ever tried to imagine an event so powerful that its effects survive a 50,000-year journey through empty space and still register as measurable on the other end? This particular burst, known as a giant flare, released in a fraction of a second roughly as much energy as our own sun produces over the course of 100,000 years. All of that energy compressed into less than 0.2 seconds. It remains the single most powerful magnetic event ever recorded, originated from outside our solar system, and its immediate effects were not purely theoretical. GPS satellites and radio communication systems experienced measurable disruption within minutes of the burst reaching Earth. In the southern hemisphere, where the night sky happened to be facing the right direction, some witnesses reported catching a brief, unexplained flash of light in the darkness, even though the source of that flash was already tens of thousands of years old by the time its light finally arrived. It was, by every measure scientists have, the most energetic event ever detected from beyond our solar system, and it originated from an object we still can't see directly, only infer through the disruption it leaves behind. So if a burst from 50,000 light-years away could nudge our satellites and briefly light up part of our sky, the next question practically asks itself: what would happen if a magnetar like this one were sitting somewhere far closer, say, right around the distance of the Moon? Let's actually run that scenario. Picture a magnetar positioned at roughly half the distance between Earth and the Moon, about 192,000 kilometers away. At that range, its magnetic field would be strong enough to instantly erase the data stored on every single credit card on the planet, all at once, with no warning. That's not a hypothetical exaggeration. That's the kind of calculation researchers have actually run. But the danger wouldn't stop at your wallet. If you were piloting a spacecraft past a magnetar at that same lunar scale distance, the magnetic field around you would be shifting so rapidly that it could trigger a phenomenon called electromagnetic induction directly inside your own body, generating an electrical current powerful enough to be lethal. It gets worse. At that same distance, the field would be strong enough to physically distort the molecular structure of biological tissue, breaking apart the chemical bonds holding water molecules together inside your own cells. This isn't a story about being pulled towards something. It's a story about your own body becoming an unwilling conductor. So here's a simple way to actually picture the number 10^15 Gauss without your brain glazing over. Since Earth's field sits at 0.5 Gauss, a magnetar is roughly 2 million billion times stronger. But the real danger isn't the strength of the field sitting still. It's how fast that field changes. Near a magnetar, you wouldn't feel yourself being pulled inward like a piece of iron toward a fridge magnet. You'd feel the current inside your own body get violently jolted by the rapid oscillation of the field around you, closer to being struck by an invisible tornado than being gently reeled in. And no, it isn't simply an oversized bar magnet either. Bring a piece of iron close and it gets pulled. Bring a laptop close and it doesn't get pulled, it gets fried. Its circuits cooked by induced current rather than dragged by any physical force. We are not pulled in. We are cooked from the inside out. Before 1998, astronomers had a problem they couldn't quite explain. They kept detecting strange repeating bursts of soft gamma-ray radiation from certain points in the sky. Objects they simply labeled soft gamma repeaters, with no clear theory for what was producing them. That changed when researcher Krisa Koveliotou and her team at McGill University pulled satellite data on one of these repeaters, SGR 1806-20, the very same object that would later produce the 2004 giant flare, and noticed something odd. Its rotation was slowing down at a rate that made no sense unless an extraordinarily powerful magnetic field was acting as a brake. That single measurement, a subtle change in rotational speed rather than any direct image, became the first confirmed evidence that magnetars were real. It's a reminder that some of the biggest discoveries in science don't come from seeing something directly. They come from noticing that something invisible must be there, because nothing else could explain what the numbers were doing. That same technique, inference over direct observation, keeps paying off. In April 2020, a magnetar called SGR 1935-2144 produced a fast radio burst, marking the first time scientists directly linked one of these mysterious split-second radio signals to a confirmed magnetar source, rather than to some unexplained event happening billions of light-years away. Magnetars are also considered a leading candidate for the origin of short gamma-ray bursts, among the most energetic events in the entire universe, trailing behind only the Big Bang itself in terms of raw energy release. And the extremity doesn't stop at magnetism. A single cubic centimeter of magnetar material carries a mass of roughly 1 billion tons, about 200,000 times denser than a block of gold that size. Could there be a more perfect natural laboratory for testing the outer limits of physics than an object we can observe from a safe distance, yet whose material properties break almost every intuition we have about matter? Magnetars aren't just the villains of this story. They are, in a very real sense, nature's own perfect laboratory, one no human engineer could ever hope to replicate. It's worth returning to that earlier claim, because it deserves emphasis. Contrary to what most people assume, black holes are not the most magnetically powerful objects ever measured. A magnetar's magnetic field outstrips anything ever recorded from a black hole, which is precisely why comparing the two isn't just interesting trivia. It's genuine correction to a widespread assumption about which cosmic objects deserve to be feared most. Magnetars don't just sit quietly generating extreme fields either. Their own radiation can superheat the surrounding gas into glowing plasma, forming what's known as a pulsar wind nebula, a structure that shines with striking intensity in the X-ray portion of the spectrum, essentially a visible signature of the destruction happening in the object's immediate surroundings. The nearest known magnetar to Earth, 1E WEN 48.15937, sits in the constellation Carina at a distance of roughly 9,000 light-years, comfortably far by any human standard, yet close enough that astronomers can study it in considerable detail. And that number, 9,000 light-years, might sound reassuring until you consider the bigger picture. Astronomers estimate there could be as many as 1,000 magnetars scattered throughout the Milky Way, yet only about 30 have actually been detected, largely because most of them are simply too faint in radio and X-ray wavelengths to spot with current instruments. That means roughly 970 of these objects, by conservative estimate, remain completely unaccounted for somewhere in our own galaxy, their positions, distances, and behavior entirely unknown to us. Our sense of safety, in other words, may be resting on a sample size far smaller than the actual population out there in the dark. Where does a magnetar's field actually come from in the first place? The leading explanation involves something called a dynamo effect, occurring in the earliest moments after a neutron star is born. A newly formed neutron star spins incredibly fast, hundreds of rotations every second, and combined with violent internal convection, that rapid spin can amplify an already present magnetic field into something almost unimaginably stronger, locking in the extreme magnetism we observe today. That birth is anything but gentle in other ways too. A freshly formed magnetar can reach surface temperatures of roughly 10 million degrees Celsius, comparable to conditions inside our own sun, although it cools remarkably fast, losing much of that extreme heat within just a few years. And the density involved defies easy comparison. A single teaspoon of neutron star material, the same stuff that makes up a magnetar, would weigh roughly as much as an entire mountain the size of Everest. Despite all this power, magnetars don't last especially long by cosmic standards. Their most intense magnetic activity is thought to persist for only around 10,000 years before the field weakens significantly, a blink of an eye compared to our own sun's roughly 10 billion-year lifespan. And perhaps strangest of all, magnetars are capable of triggering something called pair production, where the sheer intensity of the magnetic field converts pure energy directly into matter and antimatter. A process once confined entirely to theoretical physics, now observed as a real consequence of these objects' extreme fields. This is an object that lives fast, dies young by stellar standards, and leaves behind consequences that ripple across the galaxy for tens of thousands of years afterward. Now shift the focus a little closer to home. Many species on Earth rely on magnetic sensing to navigate, pigeons being one of the most well-studied examples, and if a magnetar were ever active nearby, the resulting disruption to Earth's magnetic environment could seriously disorient these animals over an extended period, throwing off migratory patterns that have functioned reliably for millennia. Would a bird instinctively wired to sense magnetic north even have a way to cope with a sky where north no longer behaves the way it always has? There's a compelling, if unproven, hypothesis floating around scientific circles that a nearby magnetar flare could theoretically trigger an event resembling the Carrington event of 1859, the historic geomagnetic storm that knocked out telegraph systems across the world. If something on that scale happened today, the consequences for power grids, satellite networks, and global communication systems would be almost impossible to overstate. Researchers at the Max Planck Institute have also found that radio signals from magnetars display an unusually high degree of polarization, nearly 100% in some cases, a rare signature suggesting an intensely twisted magnetic structure surrounding the object. Some have even speculated, though this remains unconfirmed by independent research, that a sufficiently close interaction between a magnetar's field and Earth's own magnetosphere could generate auroras visible across the entire planet, rather than confined to the polar regions we're used to seeing them in. Is it possible that something so far away, so utterly disconnected from our daily lives, could still reach in and quietly unravel the systems we depend on every single day? Our sense of stability, it turns out, may be far more fragile than we like to admit. Long before the term Magnetar existed, scientists were already staring at a genuine mystery they couldn't explain. Repeated bursts of soft gamma radiation kept showing up from certain points in the sky, earning the label soft gamma repeaters, a name that described the behavior without offering any real explanation for the cause. That mystery lingered for years until Krisa Cuveliotu's 1998 measurement of an abnormal slowdown in rotational speed finally gave researchers something concrete to work with, tying the phenomenon directly to an extraordinarily powerful magnetic field rather than any previously known process. Since then, the strangeness has only continued to pile up. On June 24, 2018, a burst from the Magnetar 1E 2589586 caused a sudden abrupt shift in its rotational period, an event astronomers call a glitch, followed by a series of X-ray signals that continued over several subsequent days. And here's a detail that quietly undercuts the assumption that modern astronomy has already mapped out everything worth knowing. The observational effort required to identify all 30 confirmed magnetars has been spread out across more than 20 years, and enormous portions of the sky remain essentially unexamined for this particular kind of object. Robert Duncan, the same physicist who coined the term magnetar back in 1992, also happened to be one of the researchers exploring the theoretical possibility of quark stars, a hypothesis suggesting that some ultra-dense neutron stars might harbor cores made of free quarks, adding yet another layer of strangeness to the already crowded catalogue of extreme cosmic objects. Isn't it strange that the same year a scientist named this dead star phenomenon, he was already chasing an even stranger possibility hiding inside similar objects? Modern science, it turns out, is still very much in the process of figuring out exactly what kind of monster it's dealing with. There's something almost comedic about the scale mismatch at the heart of this entire story. An object roughly 20 kilometers across, small enough to feel almost quaint on a cosmic map, carries 1.4 times the mass of our entire sun. It's the astronomical equivalent of discovering that the smallest person in the room is somehow also, physics permitting, the strongest by an unfathomable margin. Magnetars aren't even the only strange contender in this category either. That same physicist who named them, Robert Duncan, was also involved in exploring the theoretical possibility of quark stars, objects whose cores might be composed of free quarks rather than the more familiar neutron-packed material found in ordinary neutron stars. And inside these ultra-dense cores, something even stranger is thought to occur. A form of superconductivity unlike anything found on Earth, where electrons and protons combine to form electrically neutral neutrons, creating conditions that simply don't exist anywhere else in the observable universe. There's a certain philosophical whiplash in all of this. We spend our lives worrying about things that feel enormous in the moment, and yet here is an object smaller than most cities, quietly holding more raw physical power than nearly anything else science has ever measured. It's tempting to call it humbling, but humbling almost undersells it. For a brief moment, standing in the shadow of numbers this extreme, we are unmistakably small, and the universe in its usual indifferent way remains almost incomprehensibly vast. An object smaller than most cities. A force capable of erasing every credit card on the planet and cooking a human body from the inside without ever touching it. That contrast is the entire story, distilled into a single image. Here's what science actually offers us in the face of something like this. We might not survive an encounter with it, but we can understand it. That in itself is no small thing. There's something quietly reassuring about a species small enough to be erased by a phenomenon it has nonetheless learned to measure, name, and explain. Somewhere out there, dozens of these objects are spinning in silence, mostly unseen, doing exactly what they've always done. Our own lives, by comparison, are built around concerns that feel enormous in the moment but rarely carry any weight beyond our own heads. So if a dead star sitting tens of thousands of light years away can still reach across that unimaginable distance and erase your data, cook your body, and shake your planet's atmosphere, do your deadlines and daily pressures really deserve the size you've been giving them? Which sounds scarier to you, a star that can erase every credit card on Earth, or a life with nothing left to lose?